I've got a bit of a little bit of a question about
Yeah.
eigenvalues, eigenvectors. Does
Yeah.
the fact that all eigenvalues must be real
For Hermitian.
for Hermitian imply that there must be some real value in the eigenvectors?
Eigenvectors vector doesn't mean values.
Right, but if you could break apart the eigenvector as xi, yi, zi, then you could pull it out for the eigenvalues and they would be unreal.
Okay. Suppose you said, you mean, let's say the position operator, right? This is what you mean. Is that correct? You know, say Ri equal to, if, actually continue, we will not use I, right, as index. But since you mentioned I, so here, this is eigenvalue, right? That is real, because this is Hermitian. This one does not mean this is this just means there's a state. It may be a function, whatever, or column matrix, whatever correspond to this one. Is that your question?
Kind of. If we had, like in that scenario, we had R and then bracket notation was xi,
Oh, okay, that's
you
a,
can pull it.
you mean the matrix, right?
Yeah, inside of the matrix form.
Oh, okay.
That's a.
Oh, now I understand. So then, okay,
Yeah.
if in matrix representation, so we have this, in general, I'm going to do A1, A2, something, right? So now, since you solve that, so we do not know this is unknown. If it's like a homework, if I know, you can either use this as x, whatever you want, use I or x1 or x1 or y, whatever you use. If the first correspond to the first eigenvalue, for example, E1, right? So these are number, but this number is not eigenvalue, not this one.
Right. Yes, but I'm saying that when you end up with A times x, y, z,
These are maybe complex, may not real. This is real. That makes sense?
Yes.
That's your question, right?
Yes, but what I'm saying is if the vector are all only complex, then you can pull the I out and suddenly your eigenvalue looks like it's complex.
Oh, okay. No. Now I understand what you mean. You mean, okay, so now you have this one, is something is I100, something like this, right? Okay, so you say, okay, now I'm going to apply here as B equal to A, but now here this is A and I100, and I got I100. That's what it means?
Yes.
I don't think you can have this.
Okay, so you can't.
Or you can see this, but this means 1 multiplied.
Yeah.
The eigenvalue of A is 1. It's real. This I is still, you just take outside because it's a common factor. High speed is like this, is the coefficient, not eigenvalue. Does that make sense? So when you have this, it does not mean this one, because you see the left-hand side is this one, so right-hand side should be the same thing, it corresponds to this one. So if that equal means this one equal to 1. Okay, good. Can I erase?
Yes.
Okay, before I started, I already sent you on Blackboard mentioned the midterm exam, right? So let me mention again. Here. So midterm exam is Wednesday is 28th, right? And 2 October is 10, November 5th, right? Wednesday. So we have 1 week during the break workout this exam, and they will cover chapter 1, 2, 3, which we discussed. So chapter 1 we didn't discuss all, right? We just discussed some of the topics we discussed in these chapters. And of course, we probably cannot finish chapter 3, but just 10 to where it is, then it will cover. So we have homework. One homework is because chapter one is conceptual. Only one exercise you do at the review, right? And then we did a lot of time on chapter 2, so try to learn like a solve eigenvalue problem and all the details practice. And that will include in the exam. And the chapter 3, some of the concept here and correspond to those concepts, how to, this we are going to discuss today, like probabilities, expectation values, all this measurement. So that will include in the midterm exam. So it is take it home. I will deliver on Wednesday, and you pick up and you will turn back on this day. That makes sense? Okay. So now we keep continuing. I think postulate, we already almost deal with the postulate 3, right, that last time. It's measurement with, as you mentioned, eigenvalue. Eigenvalues of with A. So what we say mathematically, the measurement means, I think that is, right? Postulate 3. Yes. So we say that when we measure, mathematically, that means the operator A act on the initial states, and after the measurement, what happened? It will change the state from initial to another new one. That is what happened. So the quantum mechanics will not tell us what the initial states. If you do not measure, you do not know, right? So, but what we know that after measurement, we have some of the possibility give us information about after the measurement. So that is the possibility tell us what is the, okay, no, I think I'm not finished now. So this one must be one of the eigenstates, I'm going to say, since it's A, states. So that's B, go to one of the eigenstates of operator A, and the value, or the measured value, okay, of a variable value is also the one, now the eigenvalue. Here, these two are the eigenstates and the eigenvalue of the A. This is a positive 3. So that makes sense? When you want to measure the initial states, arbitrary, I do not know. But what we measured, what happened? We will change its states, initial state to the final states or to the new states, but this new state must be one of the eigenstates of the operator A, not arbitrary. And which one we are going to deposit 4 give us the probability. Then the value, which we measured, physical value, that is one of the eigenvalue of operator A, because A is Hermitian, so the values be real. They are the physical values, right? So now let's keep continue today. Postulate 4. This is what? Because here it says must be one of states or must be one of value. Now the question is, we do not know. We have to predict. So how to give us the information, the probability to find one of these, right? That is what we need to know. And the postulate give us 4 give us the answer. The outcome of this measurement. So that is us. Probabilistic outcome. Outcomes of measurement. Right, so this possibility just say it will go to one of them. So now, which states? What is the possibility that after measurement we go to eigenstates of operator A, first eigenstate or second or third? So that gave us answer this. So the probability is this, okay. So now to answer this question, but depend on these different bases. We discussed chapter 2, right? The representation for the vectors which represent represent this quantum states. Depending on the matrix representation or continuous basis, we have different representation, like column matrix or the continuous function. So now let's discuss first case. If we consider the discrete basis for spectrum, discrete. Let's say that's basis. And this is representation. So how to give this information? That means, let's say, the probability, I use the P, A means find the eigenvalue of operator A with eigenvalue AN. That is the given result I'm going to discuss. Since now that's this. Okay. So what does it mean? This is a probability of finding, okay, actually it's a probability, okay, or obtain, since with measurement, so let's get a finding of obtaining one of the first non-degenerate. If degenerate is different, non-degenerate eigenvalue eigenvalues AN of operator A hat. So that is okay, here, because it's 8, right? So that means now we know, we measure, and what the output, what we read from the measurable for the value, which is observed value which we have. So this value, you will find that's been one of these eigenvalue of the operator A. Then what is the probability that the come out is go to this one? That is this. And this one, you know, this is the initial states. Project to one of the eigenstates correspond to this eigenvalue AN, right? The denominator is normalized. Normalized is wave function, right? If it's equal to 1, then just the numerator, right? Okay, that is for this. For degenerate eigenvalues. So that case, for for the eigenvalue AN is degenerate. I think here I need to degenerate. Okay. Then the outcome for this one to find is this must be, it's not the unique, it's summation from let me use N1 from M, and this is a project of the side N J from okay. Again, you have so here, this degenerate that is degenerate, how many degenerate that is M. Suppose we have M states, we use the index J, for given N, we have additional, for given A value, actually we have 4 states, all given the AN value. That's degenerate, right? So for this case, the probability to find this one should be sum over all the possibilities, right? Project any states among these degenerate states. So that is for the non-degenerate for degenerate. And that makes sense, right, for degenerate, since you have you have the same value, but we have 4 possible states, suppose, or n possible states. So you have sum of all this together. That since those states all give us the outcome is an, right? Okay. So that is the case. Now, how about this? So if, okay, this is special case. So that is special case if the initial state is just one of the eigenstates of operator A. What happens? Come back to here. So if this is one of the eigenstates A, what will happen? Because they will go to, so they will not change, right? If this is the eigenstate of the operator A, after measurement is still there, it will not change. That makes sense?
Mm-hmm.
Okay. So, because you know this eigenvalue problem, right? It will give us AN. Right? So that state will not change. This is, if you say that is prep 1, but that's equal to psi equal to the initial one of the eigenstates. Then now I'm going to ask what is the probability in this case? Right? How much?
It would just be 1.
Yes, here, right? Because if this is the same as this one, that is 1. And the denominator also 1, right?
Yeah.
Yes. Okay. So that is the discrete base, and this is expressed. So depending on different places, we have the formula or express of this probability is different way, right? So now let's continue. Consider continue. This is, and we know what is continuous. This is like position representation, momentum representation. They are the continuous basics. So in this case, now similar to this, we are going to use different ways. So now we are going to say use lower PA. So there's no index n, since n here is continuous, right? So that means this value is continuous value, depending on which value you just select. So now this is a definition. This is a okay. This is a probability density. Density. This is a probability. And then this is the definition. So it's not really you do the derivative. Just it's the probability for given value because it's continuous. So that is density. We know that's divided by this range, right? So by definition, that is here I'm going to say operator A is for continue. Here, this is continue. Oh, okay, sorry. Since this is the case, so now A is continuous eigenvalues and they correspond each given A value we have eigenstates. Then the probability in the continuous basis, the probability state is nothing but this initial states project to this eigenstates and to the square that is known. And again, we are going to normalize, right? Because probability is 1. You have question, yeah.
I'm confused. How do you get probability density on one side of the equation and probability alone on the other side? So PA alone is probability density, and then when you take the DPA, that's probability over.
Yeah, that is just, so initially I don't want to use this one. This is really misleading sometimes. This just means that because when we say density like a volume or a density, that means this mass, total mass divided by the volume, right? Or divided by something. So if I have a quantity divided by this, the variable, this is the density. So that is something like that. So I think because text will use this one, if I were you, I just directly go to here. So this one, just kind of, we have a probability per, because continue, right? So yeah, you can say that's within the DA, we have the eigenvalue between in the small range is dA, the probability is dPA. And then divided and this gives a probability, this is the vector. When you do that, you just go to here. This gives us this how to calculate. So this just gives a concept. Okay, so sometimes since we know for the continuous, this is nothing but this psi function of A, right? So that is like the psi r, which is a state function, which is cat vector project to or represent in the position representation. So for example, since later we are going to use this, the probability to find a system at the position x. That is very simple. And that is x. If you want to here, you can also add from minus to eliminate. Okay. That is expand this explanation for this postulate 4. Last one, we have only totally 5 postulates that construct this quantum mechanics. So you see, there is not too many, but that's enough. That is so important postulate 1. So far, we all discussed this, didn't consider the time evolution of states, right? So all this, just what is how to calculate these states, what is the relation between the observable and the operator, how to measurement. Now we are going to discuss or answer the next question. What is time evolution of states, right? That is the last postulate to answer this question. Evolution of a state, a system. And this one is answered by, so that is this one depends on time. So that is governed by the Schrodinger equation. Like in the classical mechanics, we know all the dynamics is governed or controlled by the Newton's second law. Here in quantum mechanics, the Schrodinger equation. So what is Schrodinger equation? I know you're already familiar with. So now, just put here so you know where it comes from, what that means. I always use Dirac notation here. Didn't go to the detailed representation since that is just abstract discussion. And when we go to the detail, we have to select different representation space. Okay, here, Hamiltonian. And Hamiltonian actually is correspond to the energy we know, right? That is observables operator is Hamiltonian. And here, okay, I will go to details discussion in the next the remaining part. But here, just introduce this postulate here. The first, this is Schrodinger equation. Does not mean this is unique. This is in the continuum basis set. So the Schrodinger equation is divided from the continuum basis set, what we know the position representation, but from the matrix representation, or this is what this matrix representation. It is Heisenberg equation, And in the next spring, chapter 10, we are going to introduce. So here, just give you the idea, or you know, does not mean it's unique. This Schrödinger and Heisenberg developed the quantum mechanics almost simultaneously, parallelly. So one way is from this the continuum or the position representation, and he start from the free particle and derive and extend it. Heisenberg is actually from this theoretical mechanics we learn, and you know this the Poisson bracket and the equation of motion, if you remember, he from that way, and then got this dynamics of this system. Use this operator, time-dependent operator. This is a time-dependent wave function, right? So you see the difference. Here, this is the time-dependent of wave function in Schrödinger equation. Heisenberg is focused on the operator. Okay, just give you this brief introduction. Now we are going to, the remaining part, we are going to discuss each individual or interpret what is implied in physics, right? So now, let's go to the details. First, states, right? So now, let's.
So, real
Yes.
quick,
Yeah.
in Schrödinger equation, the Hamiltonian is always the total energy.
It is correspond to, yes, the Hamiltonian operator, you remember a positive 2, right? Observables has corresponding operator. So observable energy corresponding to operator is Hamiltonian.
Right. Because I know, like in classical, there were different times we had to see whether the Hamiltonian was the total
It's an
energy.
energy
or not.
function, yeah. But here is
Yes,
energy.
okay.
Yes, good, yeah. So now let's postulate 1. Let's go back to the postulate 1 about the state of system. Of a system. Let's discuss in detail. So now, according to the postulate 1, it is this one, right? Either you use time or not. You use cap. First, it is a vector. Vector in Hilbert space. It is not a vector in real space. Say, not this. Right? I think I discussed before. So that is a very important concept here, a vector in Hilbert space. And we know a vector, it may be a real function, maybe a complex function, or it may pure imaginary function, as you say, pure imaginary matrix. That is vector, that is states, not eigenvalue, not variable, not observable variables. So that's different. That is, we want to distinguish this one clearly here. Okay. And since I say this one, so just remind in chapter 2, we discussed a lot the behavior of vector in the Hilbert space, in particular, square integrable. Right? That is more important in physics. We know square integrable means the finite in space will give us the probability to find a particle that is required by physics, right? So that's why we say that vectors be in this Hilbert space. The first issue. Second one, representation, right? How to represent the vector? This is a cat, right? In this Dirac notation, just a cat. So that depend on the different representation, we have different way, right? So that is agreed. This is we already discussed. So this go to column matrix, right? So now let me say A1, whatever AN, and maybe infinite. So A N, here AN, we already discussed. AN is this, if you use A, N, this one is not different, okay. I'm going to say this is a basis. I'm use 5 here, so that is, right? So here, this number may be real, maybe imaginary, maybe complex. Not just give a coefficient, and those coefficients will form this column matrix. I will not write down, but you know, this column matrix that represents this quantum states in the discrete basis. Continue. Continuous basis. So we know, we also discuss this cat will represent by, since usually we use in the continuous space. And example, since this is a very easy to understand example in position representation. Position representation. This one we'll go to the function, right? Because position representation, if you know the basis, okay, this one is basis is, here the basis is this one, right? And in the momentum representation, the basis is the eigenvector of the momentum. Then this quantum states represented by the head project to this momentum representation with this coefficient that is. So you see, one state I can represent in different way to represent this quantum states. That is the second feature of this state of our quantum system. Okay, so number 1, 2. Now 3 is to include or contains all physical information needed. If not, meaningless, right? So that we contain all the physical information of the system. Okay. That is it, right? Number 4. This is a physically acceptable, so it does not mean all the vector in the Hilbert space can be used to represent the quantum states. Another physically required vector in the Hilbert space is physically acceptable. Need several conditions. First, it must be single value everywhere. What does mean? For example, if I have a function, this is a f(x) as a function x is like this. So for given x, I have 2 values here, right? Which one represents the quantum states? Or in other words, quantum state cannot be separated into 2. the same, they can same variables here, right?
Mhm.
So this is not acceptable. If only this one, okay, at any position we have to represent this states by 1 point. And later the next one, I'm going to explain why, right? So ask the functions be single value. If you have the not single value, it will not satisfy the function to represent the quantum states. Second one, it must be continued to at least to the first derivative. That means the required momentum must be continued. This is because the first order derivative of this wave function or the state of quantum system actually corresponds to the momentum. So that's why, because momentum speed continues, therefore that's this requires first order. Like here, if we have a function like this, that's some condition or x not equal to 0 or some point. So here it is continuous fine, satisfied first, but it is not continuous second. The first order derivative, right? One is positive, another is, the difference there. So this is not allowed physically. So when you select your the wave function to characterize the quantum states, you need to check this. Number 3. It's be finite. In the whole space. And okay, but then actually let's ask us when r go to infinity, we go to 0. So that is means this is because from where we define this is a Born probability assumption, right? So that means this one corresponds to probability. This gives a probability or probability density, and that's be finite, right? Since probability gives us how to find the system in this, if in the space, in some position, you cannot say that probability go to infinite. So because it's a finite, so we require this. This is required, right? In the Hilbert space, require this square integral. Okay. Suppose we have a function like exponential to the power is a positive. Let's go to here over x squared. This is when x go to infinite, so that is not allowed or not acceptable. And the reason is this part, because conservation of particle. Over system, right? Over particle number, okay. Particle numbers. So because we already interpreted the wave function, the normal wave function with a probability, if we integrate in the whole space, that's be 1. So that means you cannot, this is a system, if we have a total number of n particles, it will always be n, you cannot become n minus 1 or plus 1. So that is required here. Give us this physical require the wave functions be set values. Okay. Then, I think the probability I already discussed. That already introduced this class. The only thing is now is so that is the number 4, number 5. Probability density, right? Here I already just discussed before, right? So now, for the, just let me come down here. Pn. That is this, if we have this the An, Pn equal to, okay. And first write down here. Because here, probability, it always give us the maximum 1, right? Find the whole space probability to find the system ever somewhere is always 1. So we always need this one to be normalized. That is give us the total probability. Total probability. Okay, so now usually after normalize we just use this because the denominator already 1. And this usually we take a An, since An is, so what that means? If first the wave function itself, let's first normalize since physically it categorizes or describes the probability. The probability, the maximum probability, the total probability is 1 in the whole space. So if the function is not equal to 1, let's first normalize. First, that is normalize. Then we are going to discuss probability. So what is the probability in discrete? This is a discrete basis, right? That is nothing but this wave vector project to this corresponding eigenvector of or this quantum state of the operator A, and that is coefficient square. Absolute value. Probability is always positive, right? So that is, this means probability of finding the system at state. So now the question if asks us, what is probability to find a system at one of the eigenstates of operator say A, which is a set A, phi n? You have to do is you first normalize states, and then you do this the project state to the states. So the coefficient square, absolute value square, or norm of this, actually is norm of this wave function, just discussed. This interpreted norm of the function is given probability. So that is, and then for the continue, let's use the position representation. So that's B. Right definition, right? I just discussed before. Now, if normalized, it is. I'm going to say this equal to 1. So I say if normalized, it is this one, and it is nothing but this function itself, right? So this one is probability of finding the system at position R. So now, if asked what is probability to find the system at the position R, you just project this wave function to this, and of course you first need to normalize again. then that gave us. So if asked what's the probability of system find the system at a given momentum p, in general we have normalized first, normalized to 1, and then that gave us, which is nothing but the project of this wave function of a vector to the given momentum at the momentum representation. So now it is a probability of finding the system at the moment p. So depending on what kind of question ask us, you're going to find the probability. And the key is that questions be given at which basis. So correspond to that basis, we have basis vector. Right. So you need to clearly understand what the question asks. That is number 5. And there are more about this state we are going to discuss. Number 6. Imagine. What is the dimension of what is dimension? How to understand the dimension? Let's go to maybe you can go to here. Or whatever this give a probability, right? Probability dimensionless, right? So if a probability is dimensionless, therefore this square, because this is an integral with the space. Okay, let me first, since we discussed this one. Dimension of in space, not in momentum, right? So now just in the position space. So we're going to do the integral with respect to right? The whole space. This dimension is R cubed, right? Or is L cubed, right? So that is this one is L cubed if we use length. Therefore, this dimensionless, so this one is squares be L cubed inverse, right? So they cancel out. So because this square, this norm has a dimension, and then the wave function itself has dimension in a square root of L cubed. That makes sense? It has a dimension. So maybe usually if we use a square bracket, means this the dimension of this variable is this, dimension of this variable is this. It's not dimensionless because when we integral in the whole space, that is dimensionless. Number 7. Superposition principle. What that means? I mean, if any quantum states can be explained in the linear combination of, so here, if, right, so that's the superposition representation, right? And this is one of the constant, and this phi I satisfy the Schrodinger equation, because this is describe the quantum states system, the system state of the system, and then we have several systems, but we have a linear combination with a new one. How about the new one? And we'll say the new one again is one of the quantum states of system. The same system, you will have different states, right? Different states, and this the linear combination of these different states give another new state, still the state of this system. That is key. Then let's see. Let's look at this one. How about this one? Look. Let's look at this one. Does this also follow the Schrodinger equation? If yes, so this follows the same thing, right? So now I H bar partial P summation A I and final. Then AI, that's a constant, I take outside. Right? Then according to the positive 5, that's B, follow the Schrodinger equation. So this term actually is H, right? Then this constant, I can change the position with the operator. So I take operators outside. And that is nothing but itself. So that means if some of some of these states are the state of the system, then the linear combination of these states again is a state of system. That makes sense? Or the Schrodinger equation is linear. So that means a linear equation. That means this linear combination of this solution, still the solution of this equation. Since the same system, the Hamiltonian is the same, so these states, either one of them or linear combination, they all follow the Schrodinger equation. So, okay, that is all we discussed, or extended discussion about this postulate 1, how to understand or interpret the physical implication of these quantum states. So now we go to the second one is about all these other possible too, right? Variables, observables, and operators. We already know the observables. Observables are dynamically amical variables, and not measurable and be measured. So that we call the observables, like position, momentum, and angular momentum or energy, right? Something. That's classically or physically we always know that's measurable. Operator that corresponds to each observables. That assume that the postulate one is the Hermitian operator, not arbitrary operator. So that's the Hermitian operators. Okay. So now this. Let me use the columns here. So here we have R hat. Let's use the position first. So this one is R minus I reading, right? Which I described. L. So what is operator here? The energy, kinetic energy plus potential energy. What is operator here? Hamiltonian, right? Okay. So now here these two we already discussed. These two we already discussed the representation of the operator in this position representation. So now we want to know is, how about this? This function R and P, right? This is also function of, this is kinetic energy is function of momentum square. Potential energy is function of position. So that means for function, how to be function operator. That is just function operator of position and momentum. That is the variables. That is this observable is a function. Then the operator if observable is a function of momentum and position. So here, what we have to do is very easily R replaced by the operator R hat and momentum replaced by this. So now example here. Okay, now let's give us, okay, I think I already discussed, let's see. Example is Hamiltonian, right? Hamiltonian is kinetic energy operator plus potential energy operator. And we know kinetic energy is the momentum square operator plus potential. What do you do? Just do this. And the first one is minus H square. Is this. So that is for this, to answer this one. And for this one, it is also easier, right? Then, sorry, okay, just this. The operator of angular momentum, just the operator of a position, cross product is the operator momentum operator, and that is R cross minus I H bar. That's it. Okay, so those are all in position representation here. Okay, I think since we always use the position representation, let's just let's keep continuous measurement. That is okay. Now we know this corresponds to each other. Then we are going to consider measurement in quantum mechanics, postulate 3 and 4, right? Measurement in quantum mechanics. That the postulate 3 and 4 give us the explanation how the measurement happen. So now we want to discuss in details. First. How the measurement disturbed system classical mechanics, we know we can measure the position, momentum, or energy without any disturb this system. So before measurement and after measurement, the values be represented before and after will not change. Or if we consider change and not very, very small, not significant, it will not affect the result. But in quantum mechanics, okay, it is this measurement in quantum mechanics, the measurement will disturb this system significantly. That is very important. That's why we say the action right here, the action, because we know in cost 3 give us action is measurement, then you go to the new states, right? That is a change, totally change. I mean, how much change? At least we know it will change, go to one of the eigenstates of operator A if we measure this. So one example, let's consider this, if we want to measure the hydrogen atom, the electron in the hydrogen atom. So if this is S orbital or K shell and one S, right? 2S and 2P, because the shell they have the same value and the others. So you know if electron is either here or here, and the dimension is about angstrom, right? 10 to the minus 10 meter. So how to measure that? In general, in classical measurement, you cannot do that, right? This is very, very small. Even the tool of your measurement is much larger than that. So in order to measure that, we need this the radiation, right? Try to see how about if we bombard the electron from the hydrogen atom, then by how much this the energy, we can also know which energy level it is, at least. So this radiation needs a wavelength be approximately in this range. If this wavelength is much longer, you cannot measure the details about this small range, right? So that is required radiation like this, and you will see how much the radiation is a photon, right? Photon, which we say this radiation quantized. So that gave us, let's use the space here, the energy of a photon. Okay, so that is the h bar c over lambda, and that is, if lambda is this one, that is about 10 to the 4th electron volt. Very huge. So you see this huge of this energy or photon to heat the hydrogen atom, try to detect where the electron in which orbit here, then this high energy it will kick off or knock the electron out, and also this out of the orbital, original out of its orbit. Its orbit, right? So what that means, you totally destroy this position of the atom, the hydrogen atom, the position initial, the hydrogen atom electron, for example, in the s orbital. Then you want to detect whether it is there. You need a very short wavelength that corresponds to the photon, a very high energy, and what happened? It will make this electron knocked out, and then out of the orbit, so the state totally change. That is significantly, if you really want to measure that. So that is the difference of this quantum mechanics measurement and the classical measurement. Now, second, how to determine the outcome, right? That is postulate 3 or 4. And combine 3. 3 means they will go to one of the eigenstates, and value 3, one of eigenvalue, not how the probability. So let's say, okay, that is measurement, right? So initially, we do not know what state, but we can have the linear combination of where this n, okay, if I let's use a n. So here is the eigenvalue of operator A. So we have any states can be linear combination by this or expand in the space, which with this eigenvectors as a basis, right? So this is initial states. We can do that. The key is what is the coefficient an, right? Oh, sorry. I will see, because this is an eigenvalue, so this is a coefficient. Eigenvalue is not that is This one, this is the eigenvalue. Okay, now I distinguish the coefficient and the eigenvalue. So that is the positively 3, but that means, okay, so this one, okay, so this is the initial, then final, it will go to one of the eigenstates. We do not know which, but must be go to one of the not linear combination. That is the positive 3, right? And then this measured variable, A is a measurable, which we measure will be go to one of the eigenvalue of A. So now the question is probability. How to know which one? Then it gives us probability. So what this means probability? That means we measure states only with one state, one times. It will go to one of them. It will not go to give us the probability is that suppose we have a huge enough of the system ensembles, each one the same system initial. Then we measure all these ensemble together. Then some of them go to one of the eigenvalues, and I can say that some of them go to others. Then the probability to find one of them, that gives us, when we measure the probability to go to which one, which high is lower, right? So that is positive 4. So this positive 3 gives us, now the question is how to determine the outcome. That is, that is, okay, that is this one. Then I think, did I, this is the second question. Did I write on here, how to determine? Okay. How to determine the outcome. So that is interpreted like this. Then the number 3, how to predict. Predict. Then we use, let's just use this either discrete coefficient, that is, let's consider already normalized. It is a CN, good, right? C is here. That is initial state, that is not final. That means when we measure the go to finals, go to one of them, so now we are going to see if we measurement the predict the outcomes we go to one of them, what is probability? Is this one. Or the continue. We just use a continue text, right? So that is A. Then the question is, we need to know how to interpret this probability. As I say, we just use this coefficient, we can see, okay, the 10% maybe go to this state and 20% go to another state. So we need to know, this is just give us the probability, and which one will go, only after measurement we can have the answer. We just predict maybe have this probability. So now, the possible to get this one, we need to know the distribution of this probability, right? So that is distribution of probability. like this. For example, here we have a probability. I'm going to use continue. And the distribution is like a Gaussian type. And here, that is peak. This peak means if we measure several times the same system with the same initial state, like in general, we have a n's or thousands system with initial same thing, everything same. Now let's measure same times. Then what we look the output, we will see the distribution is like this. Then the maximum or the expectation value will, most probabilities happen here. So that is expectation value. Give us the distribution of this. So here, this is a fluctuation, right? Okay, let me just give you this expectation value. If we want to measure this system with the operator A, get out is output is observable A, observables, right? That is A. Now, this probability to get that observable is the expectation value to see the probability distribution, right? So that is expectation value chapter 2 we already discussed. That is the sandwich of this operator between the states. If the state is not normalized, we need to normalize. Okay, so then here, that is then the fluctuation is delta A, right? Delta A is A, that we also discussed, A square average minus A average square. That gave us the fluctuation here, right? Delta A. So now how to calculate this expectation value? Let's go to the detail, right? We already know this is if I use a phi n, this eigenstates of operator A and the A n, the eigenvalues. Then now to calculate expectation value, we have a formula. Let's keep going. I'm going to insert unity operator that is always Hilbert. Now, since this is the eigenstate of the operator A, which operator A is a Hermitian, we know this forms the complete basis, right? Because this, right? So let's look this expectation value A. Now I'm going to insert summation n, okay, by n, operator A, and another summation I'm going to distinguish m by m, cat m and bra m, denominator I just keep here, right? This one is I, another is I. So now you can see here, this A operator applied is eigenvectors, we give eigenvalues, right? So we will have, let's take the two summation outside n, m, and this one is this project of this bra to this eigenstate phi n, and the second one is give us A m. Okay, this one is the eigenstates. It's orthogonal, right? Or orthonormal. So this summation n and m, we have A m and delta n m psi. Now that means when only n equal to m, otherwise equal to 0. So the two summation become one summation. A and n, m to n, and this one. So now. So that means here you already found. Next step, if I write down another step. So here, this one is complete conjugate of this one, right? So that is what is this? Probability. Remember? Right? So now finally, expectation value is nothing but the product of the eigenvalue with its corresponding probability and sum over O. So when you ask to calculate this expectation value, you first find this, and you know the eigenvalue, so you just sum over together. No, we do not have time. Otherwise, we can go to take some example and play with this on Thursday. On Wednesday.